See this? When excited, some objects tend to keep certain vibrations that we call vibrational modes. This is the case with ropes, strings, or even plates that we used in our project. When you keep exciting such objects, they keep and pick out certain different modes they have. And this is what we can visualize with beads on plate. We use them in order to see whether in some fluids, such as the air, the beads tend to stay on the nodes of the plate, and when they're in a viscous fluid, such as water, at our scale, they tend to go on the antinodes of the plate, where the amplitude is high.
Now that we know what the phenomenon is, how are we going to record it? There are several things we had to take into account. First, we had to make sure that the plate was perfectly horizontal, so that there is no additional force applied to the beads. Second, we had to minimize reflection. And third, we had to maximize the contrast, so that the beads appear the same on the camera. The solution we found to this was to implement the following setup, in which lighting is put above so that the beads all diffuse the light in the same way. The plate is kept horizontal using a 2-axis adjustable system, and the camera is put right above the plate to reduce reflection and keep it to a minimum. This was all done in order to be later on able to track the beads using a MATLAB program.
Now we have beautiful figures, but there's nothing really exploitable. What we want to do now is to quantify the displacement and the speeds of the beads on the plate for some remarkable frequencies. Because in the end, the objective is actually to steer a bead along a chosen path on the plate. And to do so, we use a processing code on the image sequence captured by the camera.
So what we did is we picked out 30 different frequencies equally spaced in logarithm, ranging from 1 kHz to 30 kHz. For each frequency, we carried out a total of 10 experiments, and per experiment we had approximately 100 beads. Now that we have this, we followed them during the movement, and we divided the plane of the plate in different subregions according to their positions. Now, every time one of the beads passes through those subregions, we counted it and noted its speed along the x and y axis. Now, in the end, what we had is a map of the average speed of the beads versus their position on the plane.
We compared the maps drawn at 30 different frequencies and used the ones where there was a resonance. We analyzed the resonance patterns in the air and compared it to the one found in the water, and what we found is that it was the exact opposite pattern, which is what we were expecting. Out of curiosity, we also used plates of different shapes, a hexagon as well as a triangle, and after finding the resonance patterns, we used the same code to get the following maps, which speak for themselves.
So now the next step is to input all the maps in an algorithm that finds the shortest path to steer a bead from point A to point B on the plates. This method of verifying displacement has numerous applications in biological and pharmaceutical research and also in microsystem assembly, because it's very simple and it's also highly versatile because it covers a large set of resonance frequencies.